Let's take an example of insertion as well as deletion. Let's suppose we want to insert 5, 10, 15, 25, 20 and 30 in an empty red black tree. We need to insert an empty red black tree. So first we will insert 5. 5 is of red color because it is a root node. It will automatically change to black color. Now next node 10 is inserted. Now 10 is of red color. No property violation is there. Next comes 15. 5 is of black color, 10 is of red color and 15 is also of red color. Now red node has red child and uncle's color is black. So when the uncle's color is black, so we need to rotate the grandparent and it is an inline child. So this is inline child case, so we need to rotate the grandparent and it is of 10 is of red color. Now 5 is of black color and 15 is of red color, and when we rotate the grandparent we will change the color of grandparent from black to red and parent from red to black. We will rotate the grandparent, change the colors. So 10 color would be black only. Next comes next node is 25. 25 is greater than 10, 25 is greater than 15. Now 25 is here and this is, and uncle's color here is red. When the uncle color here is red, so we will change the color of parent, grandparent and uncles. So in this case 10 would be of red color, 5 would be of black color, 15 would be of black color and 25 would be of red color. But one thing we can see here that the root node has red color and root node cannot have red color in any of the scenario. So we will change the root node color from red to black because simply we can change the root node color. Next node is 20. We need to insert 20. So 20 is greater than 10, greater than 15, lesser than 20. So this is of red color, this is of red color, this is of black color, this is of black color and 5 is of black color. Now this is a property violation here. An uncle color is black and it is a triangle child. So when the uncle color is black and it is a triangle child, we will rotate the parent in opposite direction. So we will rotate the parent in opposite direction. 25 will rotate in opposite direction. (15, 20, 25). So now in this case it is again property violation here because when we follow the triangle child case we need to follow the inline child case. So uncle color is black and it is an inline child, so what we will do, we will rotate grandparent in opposite direction. So this would be 10, 5 is of black color, 20 is of black color, 15 red, 25 red and 10 is of black color. So when we rotate the grandparent, we will change the color of grandparent and parent, and grandparent color from black to change to red and 20 node color is changed from red to black. So when we rotate grandparent, we will change the scenario of, we will change the nodes. Next node is 30. We need to insert 30 in this. So 30 is greater than 10, 30 is greater than 20, 30 is greater than this. So here the 30 insertion will takes place. So when the 30 insertion takes place here, so uncle color is red. So when the uncle color is red, we need to change the color of uncle, grandparent and parent. So what is the scenario? 20 is of red color, uncle color from so this would be the tree, final tree after insertion of all the elements in the empty red black tree. So now we need to delete 10 out of these. So first of all, when we are deleting 10 out of these, we need to form the standard BST delete. In standard BST delete, both child case occurs. In both child cases, right child leftmost element is 15. So 10 would be replaced with 15. So 15, 20, 25, 30. Now you can see here that when we replace 15 with 10, so 10 would be deleted from here, so there is a double black note came here. So I can say that there is a double black note came here, that is a nil node only. So we will see the sibling color is black and inline color is red. Sibling color is black and inline color is red. So what we will do, we will swap color of we need to change the color of parent and sibling. So parent color change from black to red and red to black, and we need to rotate the parent in double black direction. So the final tree would be, we need to remove the double black and it would be become 25 will become red and 20 will become black, this is also black, and 30 will become black. So this would be the final tree we have. So in this case, when the inline child is red and uncle's color is black and inline child color is red, we need to rotate the grandparent in opposite direction, or we can say we rotate the parent in the double black direction, and we change the color of grandparent and parent, sibling and parent, and then we will form the final tree. This is how insertion and deletion in a double black in a red black tree occurs. So there is one theorem, very important theorem. The theorem says that a red black tree with n internal nodes has height at the most 2 log n plus 1. A red black tree with n internal nodes has height at most 2 log n plus 1. So what we need to prove, that we have n internal nodes, and we need to prove that when a red black tree has n internal nodes, so it height at most it would be 2 log n plus 1. So we'll start with the solution. We start by showing that subtree rooted at any node x contains at least, we start by showing that subtree rooted at any node x contains at least 2 raised to the power black height of x minus 1 internal nodes. Right? 2 raised to the power black height of x minus 1 internal nodes. Now if height of x is 0, that means x would be a leaf node, or we can say nil node. So what are the number of height? 2 raised to the power 0 minus 1, that is 0. So because there is no node there, so the height would be 0 only, right? So the height would be 0 only. So the if height of x is equivalent to 0, so the number of internal nodes would be 0 only. Now we will move on to the inductive step. Inductive step. Consider a node x has positive height and is an internal node, and it is also an internal node with 2 child, that is the x has a positive height and it is also an internal node and with 2 child. Each child has black height of either BHX or BHX minus 1. So we need to consider that each child has black height of either BHX or BHX minus 1 depending whether color is black or red. So it depends on the color of the node. The height would be black height of x or black height of x minus 1. Accordingly we can calculate. So we are assuming that each child has at least 2 raised to the power black height minus 1 internal node. So we are assuming that it is at that much internal nodes. So the subtree rooted at x contains at least number of internal nodes would be greater than equal to 2 raised to the power black height of x minus 1 left subtree. What about the right subtree? 2 raised to the power black height of x minus 1 right subtree plus the root node. This is the part internal nodes for the left subtree. These are the internal nodes for the right subtree, and one is the root node. So 1 would be cancelled out with 1. So it would be n greater than equal to 2 into 2 raised to the power black height of x minus 1. So this is nothing but 2 raised to the power black height of x minus 1. So we can say n plus 1 is greater than 2 raised to the power black height of x. So now let h, this is one point, that the number of internal nodes would be this only. Let h be the height of the tree. If the height of the tree is h, then black height of the tree must be h by 2. We can consider it as black height would be a black height is something, then tree height would be h by 2. At least itna to hoga hi, right? So we can say n plus 1 is greater than 2 raised to the power h by 2. So we are taking log both sides. Log n plus 1 is greater than equal to h by 2 log base 2. We are taking log both sides, right? So when the h would be the height of the tree, black height of the tree would be h by 2. We have put this h by 2 instead of black height in this equation. So we have got this, and we are taking log both sides. Now height would be lesser than equal to 2 log 2 n plus 1. And this is what we need to prove in our scenario. Said when the for a red black tree, the height of the red black tree with n internal nodes must be at least, at the most, this. So this would be the highest value which a red black tree has, right? Thank you for watching.